This is your sixth integration lesson. In this lesson, we're going to be looking at the application of kinematics, which is just another application of integration. On the first slide, it actually shows fairly well what we're going to be doing. It shows the connection between the distance, the velocity, and the acceleration functions, which again, from differentiation, we knew that velocity was derivative of distance or displacement, acceleration was the derivative of velocity. And I guess it stands to reason then that the reverse will be true with integration. So we integrate to go from acceleration to velocity, and integrate to go from velocity to displacement or distance. All right. Next slide. All right, so again, like I said, in kinematics so far, we've been looking at, again, the displacement, first of all, is the object's position relative to some starting point, and it can be positive or negative. Distance, however, is the total distance covered, and it doesn't matter what the reference to the starting point is, and distance cannot be negative. It's what you accumulate. Whenever you're moving, doesn't matter which direction, you're accumulating distance. The velocity, again, is just how fast, the rate of change of displacement, and the acceleration is the rate of change of velocity. And again, the picture at the bottom here shows fairly clearly what we're doing. Okay. Again, because it's derivatives going from displacement to velocity and velocity to acceleration, you should understand that it'll be integrals going the other direction. Okay. The things that we need to know in our application of kinematics is that velocity is the antiderivative of acceleration, or the integral of acceleration, like we've already mentioned. And the area under the acceleration time curve produces the velocity time curve, which I've not seen the IB test on. But displacement is the antiderivative or the integral of velocity, and the area under the velocity time curve produces the displacement time curve, and also it gives you the displacement or distance over a certain time interval, and that is obviously tested. So again, just as it shows in the orange box, and integrating between two time intervals, t1 and t2, under the velocity function will give you the displacement, all right, from t1 to t2. And if v is the velocity function for a particular particle moving along the line, the total distance traveled from t1 to t2 is given by, you'll notice here that they've put absolute value bars on the velocity function. Again, what the absolute value bars would do there is just force the function to always be above the x-axis, and then obviously its integral will always be positive. The area under the curve would always be positive, and so therefore that would give total distance. Again, as we said earlier, distance always has to be positive. All right, and this slide also does a very nice job of showing what we're doing, and it makes the connection between area under the curve and the signed area if you want. All right. So the first one is the displacement. Now displacement's very easy. You can just do the definite integral over the entire interval. You don't have to worry about regions above or below the x-axis. And if negative areas will subtract from positive areas, let's say, and that's completely fine. So in the picture to the left there, for example, this shaded area here, that'll be negative, right? And all of this shaded area here will be positive, right? And when you're finding displacement, we'll just let this negative area subtract from the positive area, and that will give a total displacement. However, with distance, again, because distance equates to area, so an area always has to be positive. Now we do have to be very concerned about regions above or below the x-axis, and we have to take those into account and know what kind of area values we'll be getting. So for example, on the interval from t1 to a, since that interval is going to be negative, we would need to deal with that and make its integral opposite, like we've already learned with some of the properties for finding definite integral. And then obviously on the interval from a to t2, that area is above the x-axis already, which would come out as positive, and so we wouldn't have to make any adjustments to that at all. And again, that's shown here. So the displacement, like I said, just perform the integral over the entire interval. Let the areas add and subtract from each other as they will. That's fine. For the distance, however, make sure you need to draw the graph, and then make areas that are negative. Take the opposite, like we did here with this, from t1 to a. All right. So the negative of the integral from t1 to a of v dt, and then on the second interval from a to t2, that part is above the x-axis, and so that can just be integrated directly. All right. The summary at the bottom is also very good. All right. So displacement is signed area, means you can use the area with its signs, and distance means positive area. All right. So it must be positive. All right. How's that going to look? Good questions. All right, so here's an example. So in the first question, it says the velocity of an object is v meters per second after t seconds, where v is given by the function 1 minus 2 sine 2t. You want the object's displacement over the first 3 pi or 4 seconds. So in this case, if I'm just looking for displacement, okay. Like I said before, I'm simply going to integrate over that time interval. I don't even have to have a picture of the graph because I don't care if areas are below or above the x-axis. So 1 minus 2 sine 2t dt. And now we just perform the definite integral. So the integral of this is t, and it's plus cos 2t. Again, make sure you can do that. Put your boundaries on the right side of the brackets, 0 to 3 pi over 4. And now do the substitution. So the substitution here will look like this. Substituting in 3 pi over 4 plus, when you multiply 2 times 3 pi over 4, you get 3 pi over 2. Parentheses here, minus, and now substitute in 0, so 0 plus cos of 0. And that will lead to the answer. So in the first set of brackets, we have 3 pi over 4 plus 0. Cos of 3 pi over 2 is 0. Again, if you need to review that, check that. And then the second brackets, it's 0 plus 1, okay? Which gives us the answer 3 pi over 4 minus 1, which can be evaluated on your calculator to be 1.36 meters. All right. Now, for the second part, for the distance traveled by the object over the first 3 pi over 4 seconds, in this part we need the sketch. All right, you need to know which regions are above and below because we need to account for those. We need to make all areas positive. So again, I've generated the graph on my graphing calculator, and if you want to do that, you can. It looks something like this. All right. And for the distance, you need to find x-intercepts. Very important. And those are going to be your intervals of integration. So you're going to find x-intercepts. Okay. And we're going to do that obviously by letting v equal 0, or setting v at t equal to 0. For this particular problem, again, I'm taking some shortcuts. but we get sine 2t is equal to a half. And again, it may be worth doing a little bit of trig review for this, but your possible answers for t are pi over 12 and 5 pi over 12 on the interval from 0 to 3 pi over 4. So pi over 12 and 5 pi over 12. So that means this first x-intercept is pi over 12. The second one is 5 pi over 12. All right. And so now when I set up my distance calculation, which will be a little bit different, the distance is equal to, it's the integral from 0 to pi over 12. Now again, that is positive already, we know that. It's area above the x-axis here in orange. Okay. So it's the integral from 0 to pi over 12 of v at t dt. The next interval is the interval between pi over 12 and 5 pi over 12. Now because that area is below the x-axis, we need to deal with that. And again, the way we can ensure that that area will give us a positive value, or that we get the positive value of that, is by subtracting. Because I know it will come out as negative, if I subtract that value, it'll then add. So then we have the interval from pi over 12 to 5 pi over 12 of v of t dt. And lastly, last amount of area is here at the end. Okay. And again, it's above the x-axis already, and so again we can just add its area. And so again we'll go from 5 pi over 12 to 3 pi over 4, again of the function v at t dt. All right. And now again you can go ahead and calculate all of these different values. The first one works out to be 0.128. The second one, after you take into account the negative, becomes 0.685. And the last part is 1.913. And if you add those all up, you get the total distance traveled. And the distance is equal then to 2.73 meters. All right. I'll show you in class how you can do these calculations by calculator. Although these are possible to do by hand, if you get exact values, they're also possible to do by calculator. So we'll do an in-class demonstration of how to use your calculator. See you in class.